I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on RC circuits, circuits with resistors and capacitors. In this video, we're going to talk about RC circuits, which are resistors and capacitors in a circuit. So what does an RC circuit look like? So first, it has a power source. You have a resistor and a capacitor. I put a branch through the middle, put a switch so that the switch can toggle between the battery and the capacitor. And initially the capacitor is uncharged, so the voltmeter across it is reading a potential of 0. When we close the switch, we're going to look at a graph of the potential of the capacitor as a function of time graph. So we want to know what shape that graph is going to take. There's really only a couple paths that the graph can take. The first is the capacitance potential is increasing at a decreasing rate, eventually reaching the EMF of the battery, or it's increasing at a constant rate, which would be a linear function. So one of these two shapes would represent the capacitor being fully charged. So it could increase at an increasing rate. That means as it gets closer to being charged, that it's going to increase the rate at which it's charging. Well, that doesn't make sense. The one that is going to actually happen is it's going to increase quicker at the beginning, and then it's not going to increase as quickly as it gets closer and closer to capacitance, because it's harder to move charge the more charge the capacitor has. So remember, charge per capacitance gives us the potential. So we're going to look at this curve, and after a long time, we know that when a capacitor is set up, that the potential of the capacitor is equal to the EMF of the battery. So that voltmeter would be reading the EMF, and the maximum value on our graph would be the EMF of the battery. Once the potential of the capacitor is equal to the EMF of the battery, so if there's no charge being moved, that means there's no current. So that means the potential across the resistor is going to be reading 0. We could hook a voltmeter up and we'd read 0 across that resistor, where the capacitor is measuring the EMF of the battery. Now we look at a graph of the potential across the resistor as a function of time. And what we know is it's going to start with the EMF of the battery, and it's going to decrease eventually to 0. But the shape that it's going to take is kind of opposite of the capacitor potential. It's going to be an exponential decay as the current reaches 0. So we're going to talk about the time constant. So it takes time for that capacitor to charge. So the time constant helps us figure out how long it's going to take that capacitor to charge. So we bring our graph back and we look at the potential versus time, and we know that we have a resistor that has a value that's measured in ohms and a capacitor measured in farads. And we know that an ohm, using Ohm's law, is going to be a volt per amp, and a farad is a coulomb per volt. Well, what happens if we multiply these two values together? We get a volt per amp times a coulomb per volt. So we know volts are going to cancel out, and that's going to give us a coulomb per amp. Now we also know that an amp is a coulomb per second. So if we substitute coulomb per second, we see that coulombs cancel out, and that gives us 1 over inverse seconds, which if we flip and multiply gives us a unit of seconds. Resistance times capacitance is seconds, and it's given a symbol of the Greek letter tau, which represents the time constant. So the Greek letter tau is the time constant, which also represents R times C. Now, note that this is the equivalent resistance and equivalent capacitance. In this simple circuit, I only have one capacitor and one resistor, but we'd find the equivalent of each to find the time constant in a more complex circuit. Now, the time constant is the amount of time it takes for the capacitor to reach 63% of the EMF of the battery. Now you may be asking, 63%, that's a very specific number. Where does that number come from? Well, in an algebra-based class, we would just be told that it's 63%, and that's really what we need to know for AP Physics 2. But what I'm going to do is I'm going to take you through a calculus derivation of how we end up with 63%. So first, we're going to start with our algebra, and we're going to write a loop rule equation for when the switch is closed. So we have the EMF of the battery, and following we have the potential across the capacitor minus the potential drop across the resistor, and that's going to equal 0. So we're going to substitute in for the potential of the capacitor. we know that the potential of the capacitor is equivalent to the charge on the capacitor over the capacitance. Now we know that the current and the charge over time is not going to be constant. So we're going to write both of those as a function of time. So now what we're going to do is we're going to write a differential equation. So again, if you're not in calculus, you can skip forward in the video. So we know that since charge is changing per time, that means current is changing per time. So we can substitute I is dq over dt into our equation times R. And now we're going to do some algebraic manipulation. We're going to divide each individual term by R. And the reason for that is we want RC in our equation because that's our time constant. So when we divide by R, it gives us our equation. And we can add dq over dt to the right side of the equation. And then the next thing we're going to do is we're going to combine our fractions. We're going to subtract the EMF of the battery over R, and that's minus Q divided by RC, find a common denominator. That's going to give us the capacitance times the EMF of the battery minus Q in the numerator and RC in the denominator, and that still equals dQ over dt. Now we're going to rearrange this equation, and we're going to factor out -1 over RC, and that'll leave us with the quantity of the charge minus the capacitance times EMF of the battery, and that still equals dQ over dt. So now we're going to go ahead and rearrange this and multiply both sides by dt to give us negative dt over RC. We're going to divide both sides by Q minus the capacitance times the EMF, and that gives us an equation that we see on the screen. Now here's where a second step for calculus comes in. We're going to integrate both sides. So the left side, we're going to integrate from 0 to t, and the right side, we're going to integrate from 0 to q. Now, integrating the left side of the equation, that's just going to give us negative t over RC, because if we substitute in, once we integrate, we substitute t, that's going to give us t over RC, and then we substitute 0, and then subtract them, well, 0 dt over RC is 0, so that gives us negative t over RC. Then, when we integrate dq over q minus capacitance times EMF, that's going to give us a natural log of q minus capacitance times EMF, evaluating from 0 to q. So let's go ahead and evaluate. Let's take negative t over RC. That's already been done. We get the natural log of q minus c times e, and that's from the q. Then we're going to subtract the 0, which is just going to be the natural log of negative c times e. Now, rearranging that equation, we know our rules for natural logs. If we subtract two natural logs, it's the same thing as dividing them. So natural log of q minus c over e divided by negative c over e, and that value is going to equal negative t over RC. Now, to get rid of the natural log, to simplify our equation a little bit, we're going to raise e to the power of that side, which e to the power of a natural log cancels out. Take the other side and raise it e to the negative t over RC. So we're done with the calculus portion now. We're just doing algebraic manipulations. So we're going to multiply both sides by negative c times e, which is going to give us this equation. And then isolating q, we're going to write q as a function of time. So we're going to add c times e to the other side, which gives us this equation. Now, remember, the ultimate goal is to find a function of the potential measured across the capacitor as a function of time. So we have q as a function of time. So if we want potential, we're going to divide both sides by capacitance. Capacitance on the right side is going to cancel out, and q is a function of time divided by capacitance, and that's going to give us the potential as a function of time. And then we can factor out the EMF of the battery, and that's going to give us an equation of V as a function of time is going to equal the EMF of the battery times 1 minus e to the negative t divided by RC, or you could substitute tau, t divided by tau. You might see the equation written that way as well. So now we have a function of potential across the capacitor as a function of time. So why is it 63%? So if we substitute RC, one time constant, in, we can evaluate that. That's going to give us the EMF of the battery times 1 minus e to the negative t over RC. we substitute RC in for t. Well, negative RC over RC is going to give us negative 1. And when you evaluate 1 minus e to the negative 1, well, that's going to give you 0.63. So this is why it's 63% charged after one time constant. Then we can repeat that process for two time constants, 3, 4, so on and so forth, and it's going to give us a different percentage, 0.86 EMF, 0.95 EMF, and 0.98 EMF after four time constants. Now, it's generally assumed that a capacitor is considered fully charged somewhere between 4 and 5 time constant because it gets pretty close to 99% charged after a fifth time constant. So that gave us an equation as potential as a function of time. Let's look at a equation for charge as a function of time. So we bring our original equation back that we derived with capacitance in the EMF of the battery, but we know that EMF or potential times capacitance, well, that's just charge. So this gives us a charging function for the capacitor to find how much charge is on the capacitor after a certain time. Using our potential as a function of time equation, we can also derive an equation for the current within the circuit. So we can just take the potential as a function of time divided by R. That's going to give us current as a function of time using Ohm's law. And we divide the other side of the equation by R. Well, the EMF divided by R, well, that's going to be the initial current when the switch is immediately closed. And then it leaves us with 1 minus e to the negative t over RC. So that's the charging function for current. So now what happens when we toggle that switch and we discharge the capacitor? So the capacitor no longer has a charge, but the charge has to move through the circuit. So we're going to have that exponential decay that we saw with the current in the circuit. So after one time constant, we have 37% of the potential still being on the capacitor. Now, we could go through the same calculus derivation, but we'd end up with an equation of charge as a function of time equals the initial charge on the capacitor times e to the negative t over RC. Dividing by capacitance would give us this equation. Potential as a function of time is the EMF of the battery times e to the negative t over RC. And if we take that equation and we divide it by the resistance using Ohm's law, well, that's going to give us current as a function of time is equal to the initial current times e to the negative t over RC. So let's look at an example problem. So we have a battery that has an EMF of 9 volts. The resistor has a value of 25 ohms, and the capacitor is 0.1 farads. And then we're going to close the switch, allowing the capacitor to charge over a period of time. And we want to know what is the current immediately after the switch is closed. So what we're going to do is we're going to write a loop rule equation for the circuit immediately after the switch is closed. So we'll start with the EMF of the battery. We know that we are going to measure a potential across the capacitor. That's going to be subtracted. And then we're going to measure the potential drop across the resistor, and that's going to equal 0. So we end up with this equation. Now, we also know that the potential of the capacitor is Q divided by C. And what we know is that immediately after the switch is closed, the capacitor does not have any charge on it. So that's going to be 0. There's not going to be a potential being read. So we can rearrange that, and the current is just going to equal the EMF of the battery divided by the resistance, or the equivalent resistance. In this case, 9 divided by 25 ohms, which gives us 0.36 amps. And that is the initial current the moment that the switch is closed. Now, what is the current a long time after the switch is closed? Well, we'll use the same loop rule equation, EMF of the battery minus the potential of the capacitor minus the potential of the resistor. Well, what we know is after a long time, the capacitor is going to be fully charged, which means there's no more charge moving. So that means that I times R is going to give us a value of 0 because the capacitor is going to have the same potential as the EMF of the battery, which means there's no more charge being moved, which means that there's no current. So I is equal to 0. Now, what is the current 4 seconds after the switch is closed? Well, in order to find the current 4 seconds after it's closed, what we need to do is we need to use the current as a function of time graph first. And what we know is that the current we know is going to decrease. So it's going to start with an initial value of I naught, which we found in the first part of example 1, and it's going to decrease to 0. So we're going to write an equation for the current as a function of time. So that's going to equal the initial current. Remember, we found that in the first part immediately after the switch was closed. So I naught, and we're going to multiply that by e to the negative t divided by RC. When our graph looks like this, that's the function. So we find current at 4 seconds. I naught we found previously, that's just going to be 9 volts divided by 25 ohms, which gave us that 0.36 amps. And then we're going to set that to e to the negative 4 seconds. And we know that R is 25 ohms, C is 0.1 farads. So multiplying that together gives us 2.5 seconds. So we can evaluate that then. So it's going to be 0.073 amps after 4 seconds. Now, remember, a time constant is 37% of the current remaining, or we're a little bit over a time constant, but not quite to the second time constant being 4 seconds. So the current should be decreased from 0.36. So the question is, what is the potential of the capacitor 4 seconds after the switch is closed? So we know that we're reading the potential now. So the potential across the capacitor, we'll look at a graph of potential of a capacitor as a function of time. And we know that it's going to reach the EMF of the battery. So it's going to have a shape like this, which means we're going to use the charging function of the potential as a function of time. And then all we have to do is substitute in 4, find V of 4, and that's going to equal the EMF of the battery, which is 9 volts. And we can substitute in the value for the time, so 1 minus e to the negative 4 seconds over 2.5 seconds. Remember, 2.5 is just R times C. That's going to give us 7.18 volts. And that value is not quite past the second time constant because it's only 4 seconds, but it's past the first time constant, so it's more than 63% charged at 4 seconds. So let's look at a second example where we have two light bulbs, light bulb A and B, hooked up with a potential of a battery. And in parallel with light bulb B, we have a capacitor that has a switch that is open. The capacitor is initially uncharged. And we want to know what happens to the brightness of the bulbs immediately after the switch is closed. So we can close the switch and we see light bulb B goes out. Well, why is that? So let's try to explain that. And what we're going to do to explain it is we're going to write loop rule equations. So the EMF of the battery minus the potential drop across resistor A minus the potential across the capacitor equals 0. And then we can write a second loop rule equation where the EMF of the battery minus the potential drop across light bulb A minus the potential drop across light bulb B is equal to 0. So we're going to use our two loop rule equations to explain why light bulb B went out. So we're going to substitute in for the potential of the capacitor. We know that's Q divided by C. Now immediately after the switch is closed, well, there's no charge on the capacitor, so that's 0. So that means there's not going to be any potential being read across the capacitor. If there's no potential being read across the capacitor and it's in parallel with B, they read the same potential. So that means there's not going to be any current going across B, and that means that value is going to be 0 as well, which is why light bulb B goes out, because in parallel the potentials are the same. So if there's no potential on the capacitor, there's no potential being dropped by light bulb B, so therefore light bulb B goes out. So a follow-up question is, what happens to the brightness of a bulb a long time after the switch is closed? So a long time after the switch is closed means that the capacitor is now fully charged. So we're going to look at our two loop rule equations again. So the loop rule equations show that now we do have a charge across the capacitor, so it's going to be reading a potential, which means that B is going to be reading a potential drop, so therefore it has to have current flowing through it, which means that's why the light bulb comes on. So as the capacitor is fully charged, that means through the switch branch, there's not going to be any charge moving because no more charge can move to charge the capacitor, so light bulb B comes on. Now, because they're set up in series, what would happen to light bulb A is light bulb A would actually get dimmer because now it's not dropping the same potential. Now, the capacitor has no current, as we mentioned, going through it. So all of the current goes through B. So it's like A and B are set up in series. So it increases the equivalent resistance. So that's why A decreases in brightness, because it drops less potential and it has less current going through it when you have a second bulb set up in series. So this is an introduction to RC circuits. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at Cabby Coaches.